Now we're ready to start applying some of these graph algorithms. Our first effort is called a minimum spanning tree. A minimum spanning tree is a graph that connects all of its vertices with the fewest number of edges. Note we're counting the number of edges. We don't care about how long each edge is. We're not looking for a shortest total length or anything like that. We're just counting edges as either being there or not being there. The minimum number of edges, call it E, is one less than the number of vertices, call it V, which gives us a simple formula for this. E equals V minus 1. The number of edges in a minimal spanning tree is the number of vertices minus 1. Here's some examples. Here on the left, we have something that's not an MST. Every vertex is directly connected to every other vertex. And you might call this a complete graph, but it's not crucial, the terminology. In the center, we have something that is an MST. We know it's an MST because if we have 5 vertices, we know that we need at least 4 edges. And as long as they're each connecting different vertices, we'll get an MST. On the right, we have a completely different MST. You'll notice it still has only 4 edges, one less than the number of vertices, but we've picked completely different edges to do it. Note there's no unique MST for a graph. Most graphs have many MSTs. How to code this? Well, the code is actually exactly the same as a DFS, a depth first search, except we need an extra print statement to print the edges that we're including in our graph. So we'll get a different MST depending on the starting point, but they will all have E equal V minus 1 edges. You can see LaFour page 644 for example code. So we pick a vertex, however we'd like, could be randomly, and then we simply start running a depth first search, and as we find connections, we just print them out, and we end up with the set of edges needed for a particular MST. So that's all there is to the minimal spanning